Sorry. Oh, I'm sorry. I set it by silence and I talked with you. Sorry. Also, I mean, Jackie, Hosan. Sorry. I thought I I thought I said to you. In fact, you didn't hear me as I have set it silence here. My micro. I have closed my microphone. You talk about biryani. Biryani. You mean the virus? Sorry. Oh no. Oh no. That's a different food. Okay. I don't know. I don't know about it. How can I keep it always here? Oh. Oh, how can I keep this? How can I keep this window always before? Do you have a chicken? Oh, you are lucky. You live together and then you can share everything together. It's a good thing. Okay, so we'll begin our class, else we'll be late. As usual, we'll have a small revision. We have talked about the software testing. We say that the testing process has two distinct goals, two objectives. Yeah, it's the third time, I think. It's the third time that we ask this question. Which two objectives of the testing process? Yeah, validation, as said by Hossam, Saddam, and validation and defect. Yeah, defect testing. Validation testing and defect testing. Yeah, in detail, the two goals, the first one is to demonstrate to the developer and the customer that the software meets its requirements, as said by Saddam, the validation. And then the second objective is to discover situations in which the behavior of the software is incorrect, undesirable, or does not conform to its specification. It said by Saddam, the defect testing. And Hosan said system testing? No, it's not an objective we have introduced in this chapter. Then we have talked about 3 conditions to decide the level of required confidence. Yeah, Saddam, very good. Three conditions to decide the level of required confidence. One is the software purpose as proposed by Saddam, and another one is user expectations. Yeah, perfect. And another one, the marketing environment. Yeah, very good. Thank you, Saddam. You have given excellent answers for these 3 conditions to decide the level of required conditions and the 2 objectives of testing process. Yeah, and we have 3 stages of testing. Typically, our commercial software system has to go through 3 stages of testing. Which 3? Development testing, yeah, very good, Saji. Development testing and other things. User testing, yeah, and another one. Performance. Not exactly. At first, we'll execute the development testing to see, to discover bugs and defects. Yeah, as said by Sajid, the release testing. After the development testing executed by system designers and programmers, then we'll begin the release testing, where a separate testing team tests a complete version of the system before it is released to users. The objective of release testing is to check that the system meets the requirements of system stakeholders. And the last one is the user testing, where users of potential users of a system test the system in their own environment. It's just before the delivery, we have the user testing. Yeah, these are 3 stages of testing. Yeah, thank you very much, Saji. Yeah, Roy and Saddam. Next one. Next one, you see it's a little different from this question, from the three stages. It's the three levels of granularity carried out during testing. Three levels of granularity during testing. Yeah. System testing. It's just then who said about it. System testing. Yeah, Hosan has said the system testing before, but not for this one. Here we have the system testing as confirmed by Saddam and others. Not exactly interface. We have said that these three levels of granularity, they are gradual. That means from it's like a pyramid, from a small unit into a big into a integral. Yeah, as stated by Saddam, unit testing. As unit testing, individual program units or object classes are tested here. Unit testing must focus on testing the functionality of object of methods. And Stagy has completed by component testing. Very good. And component testing, what are components? Components are created by several individual units. So you see, component testing should focus on testing component interfaces. So Zoe, you have said interface is, yeah, we may express it like this too, but yeah, in our book or in this slide, we talk about component testing as a component is composed by several units, by several objects. That's why we say software, as Saddam has given the definition of components. They are often composite components that are made up of several interacting objects. Yeah, so we say they are gradual. We have unit testing, then component testing. At last, we have the system testing, where some or all of the components in a system are integrated and the system is tested as a whole. So we consider them together. And system testing should focus on testing component interactions. Yeah, these are three granularity of testing during development. Yeah, we have also talked about the unit testing in detail in the last class. Yeah, we had talked about how to the definition of unit testing, how to choose the unit test cases, and yeah, I think we were here. we have talked about two possible strategies that can be effective in helping us choose test cases. One strategy is the petition testing, and another one is guideline-based testing. Now, we'll see a second granularity of testing, which is the component testing. It's here. For this one, the component testing. Software components are often composite components that are made up of several interacting objects. Yeah. For example, in our previous use cases, the weather station system, the reconfiguration component includes objects that deal with each aspect of the reconfiguration. We access the functionality of these objects through the defined component interface. Yeah. You see, it's through the component interface that we can combine different objects and realize their functionality. Testing composite components should therefore focus on showing that the component interface behaves according to its specification. And we can assume that unit tests on the individual objects within the component have been completed. That means here, when we arrive at this granularity component testing, normally we test the interfaces between different individual objects. So we assume that the unit tests have already been completed or successful. And here, we focus on the tests of their interfaces. Yeah, this figure illustrates the idea of component interface testing. Assume that A, B, C, these three components have been integrated to create a larger component. You see here, ABC compose this larger component or subsystem. Then the test cases are not applied to individual components, but rather to the interface of the composite component created by this created by combining these different or these individual components. And interface errors in the composite component may not be detectable by testing the individual objects, because these errors result from interactions between the objects in the component. So you see, when we set the test cases, we set with this the interface of the large component, not the individual component. Here, objectives are to detect faults due to interface errors or invalid assumptions about interfaces. We have 4 types of interface between program components and consequently different types of interface error that can occur. Here, I said here, objectives are to detect faults due to interface errors or invalid assumptions about interfaces. Here we have talked about 4 types of interfaces. The first one is the parameter interface. Data passed from one method or procedure to another. There are interfaces in which data or sometimes function references are passed from one component to another. And methods in an object have a parameter interface. So you see the first interface type is the parameter interfaces. And the second one, the second one is the shared memory interface. Here, we share some blocks of memory between procedures or functions. These are interfaces in which a block of memory is shared between components, and data is stored or placed in the memory by one subsystem and retrieved from there by other subsystems. And this type of interface is often used in embedded systems where sensors create data that is retrieved and processed by other system components. Like our weather station system, there we have sensors create data and then it is retrieved and processed by other system components. So we can use the shared memory interface. And the third type is the procedural interfaces. Here, subsystem encapsulates a set of procedures to be called by other subsystems. These procedural interfaces are interfaces in which one component encapsulates a set of procedures that can be called by other subsystems, by other components. And here, objects and reusable components have this form of interface. And the fourth type of interface is the message passing interface. Here, subsystems request services from other subsystems. These message passing interfaces are interfaces in which one component requests a service from another component by passing a message to it. And a return message includes the result of executing the service. And some object-oriented systems have this form of interface, as do client-server systems. Even for these 4 types of interfaces, you see they are different. They are at different level. The first one is about the data passed from one method or procedure to another. That's why we have the parameter interface. Then we talk about the procedures or functions who share together some blocks of memory, shared memory interfaces. Then we have the procedural interfaces to encapsulate subsystems, and later we have the interaction between different subsystems. That's why we have message passing interfaces. Yeah, these are 4 types of interfaces at different levels. And interface errors are one of the most common forms of error in complex systems. These errors fall into 3 classes. The first one is the interface misuse. A calling component calls some other component and makes an error in its use of its interface. Like parameters in the wrong order. Yeah, it corresponds to the first type of interface, which is the parameter interfaces. And this type of error, is common where parameters may be of the wrong type or be parsed in the wrong order, or the wrong number of parameters may be parsed. So we have this class of error, interface misuse. And the second class is the interface misunderstanding. Here, a calling component embeds assumptions about the behavior of the call component, which are incorrect. You see, here we talk about the interaction between different components. We have the calling component and the called component, and the calling component consider the behavior of the called component as incorrect. So a calling component misunderstands the specification of the interface of the called component and makes assumptions about its behavior. And the called component does not behave as expected, which then causes unexpected behavior in the calling component. For example, a binary search method may be called with a parameter that is an unordered array, and the search would then fail. Do you remember the binary search algorithm? You remember it? The binary search algorithm. No answers for binary search algorithm. I think, Roy. And what's the parameter passed in this binary search algorithm? What kind of parameter do we pass for this kind of algorithm? You can consider binary search is a fast search algorithm with running complexity. It's a fast search algorithm with a runtime complexity. Okay, thank you, Saddam. And what we are talking about is the parameter passed in this algorithm. Do you have some ideas about it? Yeah, array. Um, and an array of data. And what's the particularity of this array of data? Exactly. Yeah, Roy, you are right. We use a sorted array of data as parameter in this, yeah, a sorted array by repeatedly dividing the search interval in half. Yeah, you are right. Thank you, Roy and Saddam. Yeah, that's why here with this algorithm, if a binary search method is called with a parameter that is an unsorted or unordered array, then the search would be fail and it creates the interface misunderstanding error. We have the third type of error is the time errors. The code and the calling method and the calling component operate at different speeds when the out-of-date information is accessed. Here, this kind of error is usually this kind of error occurs in real-time systems that shared or that use a shared memory for or a message passing interface. The producer of data and the consumer of data may operate at different speeds. They have different speed, so we have we can access the out-of-date information, and unless particular care is taken in the interface design, the consumer can access out-of-date information because the producer of the information has not updated the shared interface information. This is the third class of errors, interface errors. You see, testing for interface defects is difficult because some interface faults may only manifest themselves under unusual conditions. For example, say an object implements a key as a fixed length data structure, and a calling object may assume that the key is implemented as an infinite data structure and may not check for key overflow when an item is entered. And this condition can only be detected during testing by designing test cases that force the key to overflow and cause that overflow to corrupt the object behavior in some detectable way. Mm, yeah, we have some general guidelines for interface testings. Perhaps we'll talk about it later. Now, I will. Mm, I'm sorry. Normally, we'll yeah, I will note for your attendance now. If you want to have a break, you can have a break. Hi, we are back. Can you hear me? We are back. I have noted the attendance and we have 2 absence today. Okay, thank you, Malala. Um, yeah, so we'll continue. We have talked about four, four types of interface error and three, yeah, and we can, for these three, we can classify these errors into 3 classes. And now we'll talk about the general guidelines for interface testing. The first guideline is design tests so that parameters to a code procedure are at the extreme ends of their ranges. Yeah, it means that we can examine the code to be tested and explicitly list each core to an external component. We can design a set of tests in which the value of the parameters to the external components are at the extreme ends of their range. And these extreme values are most likely to reveal your inconsistencies. Yeah, inconsistencies. You see, this one will effectively solve the error of the interface misuse. Yeah, that means the type of parameter interfaces we can solve this type of errors with this guideline. And the second guideline is to always test pointer parameters with non-pointers. Where pointers are passed across an interface, always test the interface with non-pointer parameters. The third one, for these non-pointers, in Java, we may commonly face this error. Also, I think in C# or other object-oriented programming language. The third guideline is to design tests which cause the component to fail. Where a component is called through a procedural interface, design tests that deliberately cause the component to fail. And differing failure assumptions are one of the most common specification misunderstandings. So we need to design tests which cause the component to fail. And the fourth guideline is to use stress testing in message passing systems. This means that we should design tests that generate many more messages than are likely to occur in practice. In this way, we can reveal timing problems. That means the third class of errors, timing errors. And the fifth one is in shared memory systems, vary the order in which components are activated. Where several components interact through shared memory, design tests that vary the order in which these components are activated. These tests may reveal implicit assumptions made by the programmer about the order in which the shared data is produced and consumed. Yeah, when we develop some systems, sometimes the order of execution or the order of the parameters or even some objects may change the result of our system. That's why here what we say, in some situations we need to vary the order. Okay, this is for the interface testing. Now the component testing. Now we'll continue with the next part, which is the system testing. For the system testing, Rama, you are there? So I need to note for your attendance. You don't answer me? You have answered. Okay, I have at in the first part of our class you were not there, I think. And I have a question for you. If you can, yeah, if you can answer it correctly, then I'll give you 4 attendance. Else, it's a half attendance. Okay. Because I'm not sure if you were there with us for the first part of our class. So this is our test to see if you were there with us. Kamruzama, you hear us? Or you disappeared, so you don't want your attendance? Or you have the problem of network, your net? Uh-oh, Kamruzama is disappeared. Okay. We'll have a revision later. We'll continue with our system testing. As we say, we have unit testing, component testing, and system testing as a pyramid. System testing, we consider the system as a total. Now we'll see it in detail. System testing during development involves integrating components to create a version of the system and then testing the integrated system. The focus here is to test the interactions between components. Yeah. For the component testing, the focus is testing the interface between objects. And for the system testing, the focus is to test the interactions between components. You see, the hierarchy here is very clear. And system testing checks that components are compatible, interact correctly, and transfer the right data at the right time across their interfaces. So it obviously overlaps with the component testing, but there are 2 important differences between component testing and system testing. Okay, here, system testing tests the emergent behavior of the system. As we say, when we integrate different components, we may have some emergent behaviors. Mm, yeah. Here, just then we say that components testing and system testing, they overlap in some degrees, and but there are two important differences. The first difference is that during system testing, reusable components that have been separately developed and off-the-shelf systems may be integrated with newly developed components, and the complete system is then tested. This is for the system testing. And the components developed by different team members or groups may be integrated at this stage. System testing is a collective rather than an individual process. In some companies, system testing may involve a separate testing team with no involvement from designers and programmers. Yeah, you see, with the component testing, normally we separate them. We separate different individual components and check them individually. And for the system testing, we compose them and we integrate different components or different subsystems. Then we test the complete system. So that's why we say system testing is a collective process. Here we have shown the yeah, two important differences between system testing and component testing. When we integrate components to create a system, we get emergent behavior, as we have said before. This means that some elements of system functionally some elements of system functionality only become obvious when we put the components together. And this may be planned emergent behavior, which has to be tested. For example, we may integrate authentication, authentic authentication component with a component that updates information. We then have a system feature that restricts information updating to authorized user. You see, when we separate these two components, it's okay. It's our authentication component and our updating information component. But if we compose these two components, we may have some emergent behavior. So we have to develop tests that check that the system is only doing what it is supposed to do. Therefore, system testing should focus on testing the interactions between the components and objects that make up a system. We may also test reusable components, as said here. Reusable components or systems to check that they work as expected when they are integrated with new components. This interaction testing should discover those component bugs that are only revealed when a component is used by other components in the system. And interacting testing also helps finding misunderstandings made by component developers about other components in the system. Yeah, here it's for the difference between system testing and the component testing. Mm, because of its focus on interactions, use case-based testing is an effective way to system testing. Now we will see this use case testing in detail. The use cases developed to identify system interactions can be used as a basis for system testing. Each use case is implemented by several components or objects in the system. So that's why here we say each use case usually involves several system components. So testing the use case forces these interactions to occur as we consider only the integrated system. And the sequence diagrams associated with the use case documents the components and interactions that are being tested. You see, testing the use case here forces the interactions to occur. And when our if we develop a sequence diagram to model the use case implementation, we can see the objects or components that are involved in the interaction. That's why here we say the sequence diagrams associated with the use case documents, the components and interactions that are being tested. Here, this figure shows the sequence of operations in the weather station when it responds to a request to collect data for the mapping system. This sequence diagram, we have seen it before. I'm not sure if you remember it, but it is the sequence diagram of our previous example, the wilderness weather station system. The weather station is asked to here it is asked to report summarized weather data to a remote computer. We can use this diagram to identify operations that will be tested and help design the test cases to execute the tests. So ensuring a request for a report will result in the execution of the following threshold method. Here, mm, yeah, you see at first we have satcom here. We get a request, and then we have the weather station, we have the report weather, then this object comes link, get summary, and the weather data summarize. You see, with this sequence diagram, it helps us to design the specific test cases that we need as it shows what inputs are required and what outputs are created like this you see the input and then we'll get our output. An input of a request for a report should have an associated acknowledgement. A report should ultimately be returned from the request. And during testing, we should create summarized data that can be used to check that the report is correctly organized. And an input request for a report to weather station results in a summarized report being generated. We can test this in isolation by creating raw data corresponding to the summary that we have prepared for the test of SATCOMs and checking that the weather station object correctly produces this summary here. This raw data is also used to test the weather data object, this part. Mm, yeah, of course, here we have simplified the sequence diagram in this figure. So it does not show exceptions. Normally, a complete use case or scenario test must also take these exceptions or other things into account and ensures that objects correctly handle exceptions. Yeah, here is the example of our sequence diagram. Mm, for most systems, it is difficult to know how much system testing is essential and when we should when we should stop testing. Here, as said here, exhausted system testing is impossible, so testing policy, which define the required system test coverage, may be developed. Here, exhaustive system testing, that means every possible program execution sequence is tested. So this testing the testing has to be based on a subset of possible test cases. For example, all system functions that are accessed through menus should be tested, and combinations of functions text formatting that are accessed through the same menu must be tested. Where user input is provided, all functions must be tested with both correct and incorrect input. These are for some testing policies. Yeah, normally these test, that means determines which which we need to keep we need to take into consideration, which not. These things, they may be based on experience of system usage and focus on testing the features of the operational system. Now we'll see an approach to program development in which we interleave testing and code development. It is the test-driven development. As said here, test-driven development is an approach to program development in which we interleave testing and code development. Um, For a test-driven development, tests are often written before code, and passing the tests is the critical driver of development. We develop the code incrementally, along with a test for that increment, and we don't move on to the next increment until the code that we have developed passes its test. Here, these essential points make us remind us about agile approach. Do you remember? Yeah, here we say test-driven development was introduced as a part of agile methods such as extreme programming. However, it can also be used in plan-driven development processes. You see here test-driven development. Oh, this figure shows the fundamental test-driven development process. We have one, two, three, four yeah, four steps here, but in total, we can say we have 5 steps. We stop, we start or we begin by identifying the increment of functionality that is required. And this one should normally be small and implementable in a few lines of code and to identify the new functionality. Then we write, the second step is to write a test for this functionality and implement this as an automated test. It means that the test can be executed and will report whether or not it has passed or failed. It's for the writing test. Then we can run the test along with all other tests that have been implemented. Initially, we have not implemented the functionality, so the new test will fail. This is deliberately, it shows that the test adds something to the test set. So we can, yeah, here, normally as we have said before, the new test will fail. And then we implement the functionality and rerun the test. So we go back here to run the test. This may involve refactoring existing code to implement it and add new code to what's already there. And once the test runs successfully here, we move on to implementing the next chunk of functionality. So you see here we have the first step, second one, third one, fourth one, and the fifth one. These 5 steps in the process, in the test-driven development process. Yeah, perhaps I will try to revise some, get some summary, else you will. Some of you perhaps found it too boring to hear it like this. Me too. And the question with Kamruzama, your your return back or your, yeah, I think it's too boring if we talk about it like this. And Kamruzama, not here. Okay. Um. So we'll begin by this question for Kamruzama. We have talked about 3 classes of interface errors. Do you remember these 3 classes of interface errors? Saddam says the 3 interface misuse, interface misunderstanding, and time errors. Perfect. Thank you, Saddam. Yeah, these are 3 classes of interface errors. A similar question. Yeah, with a very similar question is that here we have introduced 4 types of interface error. Do you remember 4 types of interface error? Do you have some ideas about these 4 types of interface errors? Parameter interface. Thank you, Saddam. Yeah. Shared memory interfaces. Perfect. And 2 others, procedural interfaces. The last one, and message passing in interfaces. Yeah, excellent. Thank you. Yeah, Saddam. Here, you see these 2 classifications are very similar. The first one, yeah, we talk about 4 types of interfaces. That means, yeah, this classification depends on the interfaces between program components. As we say, for component testing, we focus on the interface between different units. Here, the 4 types of interface errors depends on the different type of interface between program components. That means different units or different objects. That's why we can have parameter interface, shared memory interface, procedural interface, and message passing interfaces. We see parameter interface is it's just for some interfaces in which data or sometimes function references are passed from one component to another. And for the shared memory interface, it corresponds to interfaces in which a block of memory is shared between components. So you see here, for the second type, we have some memory in share between components. And the third types of interface errors are procedural interfaces. It corresponds to interfaces in which one component encapsulates a set of procedures that can be called by other components. So you see, there are some dependency relationships between the components. One component may call other components. This is for the procedural interfaces. And the last one is the message passing interfaces. Here, this type of interface errors correspond to interfaces in which one component requires a service from another component by passing a message to it. You see, even these last 2 types, they are similar. They have a calling component and a called component, but the difference between them is here. For the procedural interfaces, we haven't specified the message But for this one, we have talked about we have talked about a service also by passing a message. That's the difference between these two types of interface. And for the three classes of interface errors, yeah, it's not this depend on the types of interface anymore. It's talk here this one we talk about the interface errors said by Saddam here with these three classes of interface errors. We have also how to say these three classes of errors, they correspond to four types of interfaces too. For the first one, interface misuse. The most of time it talks about the first type, that means the parameter interfaces. As here, the interface misuse, it means a calling component misunderstood. Yeah, a calling component calls some other component and makes an error in the use of its interface. It's always with the parameter interfaces. And for the second one, interface misunderstanding. This one, yeah, here we may have the procedural interfaces or message parsing interfaces. We may correspond to different types of interfaces. And the third one, timing errors. This is the particular. It is always occur in real-time system that uses a shared memory. So you see this class of interface errors correspond always to the shared memory interfaces. Yeah, here I have accentuated the differences between these two classifications and these different components. If you have some questions, don't hesitate to ask here. And later, if we pass, then it will be more difficult to come to return back. Okay, a last question before the ending of the class is how to describe this figure, which shows the fundamental test-driven development process. How to describe it? Anyone has some propositions for this process? How to explain this process, this test-driven development process, as shown in this figure? We have explained it before, and now, do you remember how to explain it? We say we have 5 steps. Which 5? Wow, so dumb. Start by identifying the increment of functionality that is required. This should normally be small and implementable in a few lines of code. And write a test for this functionality and implement this as a uh, why you retrieved it? Yeah, it yeah, you have found the answer precisely. An approach to program in which we interleave testing and code development. Tests are written before you develop code incrementally. No, this one. You have found the electronic version. No, it's okay. But here, what you have just then, what you have sent it's perfect. It's okay to explain this figure, the test-driven development process. But this part, this one is for the definition, the definition of test-driven development. It's not the description of the process. It's perfect if you have found the electronic version, then you can revise it and review it by yourself easily. Hmm, yeah, not exactly this one. Oh, you have retrieved it again. Um, okay, for this part, in fact, the first step is just this case, this frame. That means we identify the increment or functionality that is required. No, it's okay, Saddam. Um, yeah, this is the first step to identify the incremental functionality that is required. And then we write a test for this functionality and implement it as an automated test. Automated test, we have explained it before. Later, the third step is to run the test. Yeah, we run this test. Initially, we have not implemented the functionality, so the new test will fail. So it's here. We are, I'm sorry, I'll keep it here. So we need to implement the functionality and rerun the test. Yeah, we rerun the test like here. This is the third step. The fourth. This is the third step and the fourth step. We'll rerun the test. Once our tests run successfully, then we can go on to implement the next new functionality. This is the fifth step. That's the 5 steps in this test-driven development process. Is it okay? Okay, and others, do you have some questions or some doubts, something you want to say? Saji, okay. If you don't have any other questions or anything you want to say here, we'll stop here. Until here, I cannot see Kamruzama. I'm not sure if he's with us or not. We have any assignment today? No, not for today. Not today, but tomorrow we have assignment and yeah, tomorrow. Kamruzama is not here. Okay. So I'll say goodbye to you. Have a good time and thank you for your cooperation. Thank you for your intention. Bye bye. Bye.